Hi, in this video, we will be introducing some linear algebra concepts. Most of these you are already aware of, but we are trying to refresh our memories and we'll be trying to connect some of the data science concepts that we will be building moving forward. Okay, so the outline is we will talk about some distance or proximity metric, namely L1 distance or L2 distance and cosine distance. And then we will connect these distance metric concepts to one of our first machine learning model, what we call K nearest neighborhood model. Okay. Again, to do this modeling, we will also need to learn the concept of vectors. Okay. So three major points: distance or proximity metric, K nearest neighborhood model, and some of the basic concepts about vectors and vector spaces and also the vector operations. So these will be our main content for this lecture. Let's we are given these two data points on a Cartesian plane. One is the green point and one is a blue point. Okay. And now we have another point, that is the dotted point here. And we need to decide whether this new point is actually closer to the blue point or the green point. So intuitively, mainly visually, we can infer that this new point is actually closer to the blue point. But how do we quantify this? Okay, so here we will use the distance or proximity metric. And I think most of us are aware of some standard distance metrics. So we are going to quantify the distance metric. And as I was saying, these 2 points were given on a Cartesian plane. So let's actually first identify their location on the Cartesian plane. So if you denote these blue points as x1, y1, and then the green point as x2, y2, and the new point is x3, y3, then the distance or the proximity of this new point to the other two given points can be estimated by some distance metrics. And one distance metric we learned in our high school math, what we call the Euclidean distance. So this Euclidean distance is also known as L2 distance in the data science community. And here is what the formula is. Okay, so the P1 is x1, y1, and then P2 is x2, y2. Then the Euclidean distance or the L2 distance is just the axis-wise difference, then square. So x2 minus x1 square, then y2 minus y1 square, and then you sum it and then you take the root. As this point is actually at 0, 0 location, we can just say that for these 2 points, given points, this L2 distance is just the x2 square plus y2 square, then square root. Okay. So the Euclidean distance is also known as L2 distance. Okay. We are actually already aware of the L2 distance or the Euclidean distance, but there are many other distance metric definitions available. And one of the second one is the L1 distance. Okay. So L1 distance, the absolute difference between x2 and x1 plus y2 and y1. Pictorially, L2 distance is the red line and the L1 distance is just the blue two sides of the triangle. Okay. So we now know two distance metrics, L1 distance and L2 distance. Here I'm showing some examples. You can check whether the calculations are right or wrong. Now, if you are comfortable with the definition of a distance metric, then we will use those distance metric to define our first machine learning model, what we call K nearest neighborhood model. In summary, this is a supervised non-parametric model, and it can be used for both classification and regression tasks. Okay, so this is our first model, and this is purely based on the distance metric definition. So as we have learned two distance metrics, the L1 distance and L2 distance, Let's look at this particular example. So I have taken this from the Wikipedia. So imagine that we have some red triangles and blue squares. So this is our data set. And now we have a new unknown green point, okay? Recall that we have a k and then nearest neighborhood model. So the parameter here is the k. So if you think that, okay, I want to do a 3 nearest neighborhood model, then the idea is that you have to find the closest 3 data points. So these, the 1, 2, and 3. And then if you take the closest 3, then your prediction outcome would be a red triangle, because the red triangles are majority of these 3 known data points, okay? But here the basic principle of k nearest neighborhood model, by estimating the distance between the data points. You have a new data points, you estimate the distance for the available data points, and then you make your decision. It's a quite naive, simple model, okay? For the k nearest neighborhood model, you see that the outcome of the model would be a red triangle. But interestingly, if you take a 5k nearest neighborhood model, so that means that k equal to 5, then you see that now the outcome or the decision is changing, because now we have a majority of the data points are with blue square, okay? Again, the whole point is, as we learned the distance metric definition, we also learned the k nearest neighborhood model. This is good, okay? So we know about L1 distance, we know about L2 distance. Now we will be learning about another very important distance metric, what we call the cosine distance, okay? So the cosine distance, what we call the angular distance. So imagine that we have 2 vectors A and B, and then the cosine distance will be estimated by taking the dot product of A and B and divide by the corresponding norm of each vectors A and B. We'll be learning about how to do the dot product and how to do the norm estimation in another video, okay? If you have one vector 0, 0, then the cosine distance becomes 0, okay? So this is one thing. And if we look at the cosine distance between 2, 3 and negative 1 and 3, then we see that the distance become negative, okay? So you might imagine that how can the distance become negative, you know? And that's why this distance metric is quite special, you know? And we will see more examples, okay? What's your interpretation of negative distances? Because this might be unfamiliar to some of us, okay? So there are certain rules. So if 2 vectors are proportional, that means that they are in the same direction. You can see that the blue vector and then the red vector are actually on the same line and both have same direction, you know. So both the vectors are on the positive side of the x-axis, okay? So if you take the cosine distance of these 2 vectors, then their value will be 1, okay? You can do the math as we have given the equation before, okay? If you have orthogonal vector, then the cosine distance will be 0, okay? So just follow the rules, okay? If they are on the same side and same direction, they will be having cosine distance 1. If they are orthogonal, they will have cosine distance 0. And if they are on the opposite direction, so for example here 3, 0 and negative 2, 0, they are actually on the opposite side of the y-axis, okay? They are actually pointing towards completely two different direction on a 180 degree angle, okay? So in that case, the cosine distance will be negative 1. So the cosine distance range is negative 1 to positive 1, you know. And why it is unique? Because in distance metric, if the value is within 0 and 1, then you can just estimate the proximity, you know. But here, in some cases, we will have spatial information to encode. For example, you can say that, okay, this guy is actually completely opposite to the pink guy, okay? So you can see that these positive and negative sign are actually giving additional information to the model, okay? So we'll learn more, but today the main focus is we learned about 3 different distance matrices, L1, L2 and cosine, and one model that actually purely works with distance calculation, okay, because if you know how to estimate the L1 or L2 or cosine distance, you can write your first model, that what we call as k nearest neighborhood model, okay. If you are not clear about any of the distance definitions, please reach out to us. But the main focus was to learn three distance metric definitions.